On October 29, 2025, interstellar visitor 3I/Atlas flared so bright near the Sun it defied every expert prediction, right as a barrage of monster solar eruptions raged across the far side. Scientists rushed to check the comet's path, not a hint of deviation. If Alert 3I/Atlas went super bright and it's terrifying, sounds sensational, the real danger might be above our heads, not speeding in from the stars, but brewing on our own sun. What exactly happened as space weather and an alien wanderer collided? The answers could change what you expect in the days ahead. At one point, 36 astronomical units from the Sun, 3I/Atlas, crossed its closest approach on October 29, 2025. The energy environment at that distance is not subtle. Solar irradiance reaches about 735 watts per square meter, a level that dwarfs the deep space background by more than 15 orders of magnitude. For comparison, the same object drifting between stars would experience less than a 10 millionth of a watt per square meter, barely enough to warm a grain of dust. This sudden exposure to intense sunlight is what drives most comet activity. As a comet nears the Sun, surface ices heat up and begin to sublimate, releasing gas and dust into space. For 3I/Atlas, the thermal load at perihelion should have triggered a predictable rise in brightness, following models built from decades of observing Oort cloud comets. The numbers are straightforward. At 1.36 astronomical units, solar energy is about 54% what it is at Earth's orbit, more than enough to power outgassing and dust jets. Yet, the observed brightening far exceeded what this energy input alone could explain. The baseline physics, solar flux, heliocentric distance, and standard sublimation rates set the stage but left a gap between expectation and reality. As the comet moved through this raw solar environment, it became clear that something beyond simple sunlight was at work. The need to look for external triggers, not just intrinsic comet activity, became unavoidable. Between October 19th and 29th, the Sun's far side unleashed a relentless sequence of powerful coronal mass ejections. Helioseismic mapping revealed that several active regions, already sprawling and unstable, were expanding and merging out of sight from Earth. Over 10 days, multiple CMEs erupted in rapid succession, each carrying billions of tons of plasma and magnetic field into the inner solar system. These eruptions weren't minor events. Several reached speeds exceeding 1,200 kilometers per second, fast enough to sweep up ambient solar wind and carve shock fronts through the heliosphere. Solar monitoring teams tracked these far-side blasts using stereo A and helioseismic data, piecing together the evolving solar landscape. Some of the largest ejections were modeled to cross the orbital path of 3I/Atlas just as it neared perihelion. While the comet was hidden from ground-based telescopes, the timing of these solar events raised the possibility that Atlas was directly exposed to multiple CME impacts within hours of its closest approach. The significance of this barrage goes beyond sheer frequency. As active regions grew and merged, the Sun's magnetic complexity increased, creating a turbulent environment for any object passing nearby. Each CME delivered a surge of energetic particles and fields, conditions known to trigger dramatic changes in cometary comae and tails. The overlap between this solar storm window and the comet's sudden brightening pointed to a critical external influence, one that could not be explained by sunlight alone. This 10-day eruption cluster set the stage for the extraordinary photometric evidence that followed. Photometric analysis of 3I/Atlas near perihelion revealed a brightness curve that stands out even among the most active comets. Using stacked coronagraph data from SOHO's C2 and C3 instruments, along with Stereo-A's CCOR-1, astronomers measured the comet's apparent magnitude as it approached and rounded the Sun. The results were striking. The rate of brightening followed a power law close to R to the -7.5, with an uncertainty of about 1. This value is more than double the typical R to the -3 or 4 seen in Oort cloud comets, and far steeper than any pre-perihelion model had projected for an interstellar object. The photometric pipeline combined multiple color filter stacks, blue, orange, and clear, each sensitive to different molecular emissions. The blue stack, in particular, captured strong C2 swan band emissions, while orange was dominated by NH2. Both showed the comet shining up to 0.7 magnitudes brighter than in clear, indicating a surge in gas-driven activity. These measurements were cross-checked between instruments, with CCOR-1 readings offset by 0.4 magnitudes to align with the C3 clear baseline. Systematic uncertainties from background subtraction and aperture choice were carefully considered, but even the most conservative error margins could not account for the steepness of the observed slope. This R to the -7.5 curve means 3I/Atlas's total output increased by more than a factor of 300 as it halved its distance to the Sun. The anomaly was not a subtle uptick, but a dramatic and sustained rise, captured across independent datasets. Such a rapid escalation in brightness demands a mechanism beyond normal solar heating, setting the stage for deeper questions about what triggered this outburst. Every major comet outburst raises the question, did something nudge its path? For 3I/Atlas, the answer comes from a careful watch on the numbers. On October 29th, as the comet rounded the Sun at 1.36 astronomical units, the NASA JPL Ephemeris team released their latest orbital solution. Using position data from SOHO, Stereo A, and other space-based assets, they compared the comet's actual track against the predicted hyperbolic path. No measurable deviation appeared. The calculated position matched the model within the expected margin of error, even after the surge in brightness and the barrage of solar activity. This means that, despite the dramatic outgassing and possible mass loss, 3I/Atlas did not alter its course. Its velocity and trajectory still fit the profile of an interstellar visitor, not a solar system object. The hyperbolic excess velocity, what marks it as unbound, remained unchanged. JPL's orbital solution, time-stamped to October 29th, confirmed that the comet would continue outward, on track for a Jupiter-side exit from the solar system. For planetary defense teams and the public, this is the key point. There is no evidence the object is on a collision path with Earth or any planet. The integrity of the trajectory, checked by independent analysts and cross-validated with multiple instruments, rules out any sudden threat from the comet itself. The story, for now, is not about a rogue object veering off course, but about the indirect risks that come from the Sun's activity and the space weather environment. The focus shifts from orbital mechanics to what solar eruptions might do as active regions rotate Earthward in the days ahead. Detecting a faint interstellar visitor against the glare of the Sun demands more than just advanced hardware. It requires a network of determined observers and the right tools to tease a signal from noise. As 3I/Atlas slipped behind the Sun, ground-based telescopes lost sight. But spaceborne coronagraphs, SOHO's C2 and C3, Stereo A's CCOR-1, kept recording. The comet's image, buried in streams of solar wind and coronal haze, was not visible in a single frame. Instead, astronomers, many working from home labs and amateur collectives, turned to a method called shift and add stacking. This technique involves aligning and layering dozens, sometimes hundreds, of images along the predicted path of the moving comet. Each frame on its own may show nothing but background glare, but stacking them, with the right offset for the comet's motion, lets the faint signature build up while random noise fades away. In late October, two amateurs, working independently, detected the first sign of the outburst using this approach. They compared their results in real time over a Discord channel, sharing raw data and processing scripts. Their stacks revealed a clear, repeated brightening in both the C3 blue and orange filter sets. Evidence that with careful technique, even non-professionals could contribute to the discovery. The results didn't stand alone. Professional teams ran their own reductions, using similar stacking routines and cross-referencing the amateur findings. Multiple datasets, each processed separately, converged on the same photometric curve. This redundancy and the transparency of the workflow built confidence in the measurements. Space-based assets provided the raw images, but it was the collective effort, citizen scientists and professionals together, that made the detection robust. The numbers held up under scrutiny, setting a solid foundation for analyzing the comet's physical changes in the days that followed. The physical structure of 3I I/Atlas, as revealed by coronagraph and heliospheric imager data, stands out as much as its brightness curve. Instead of the classic symmetric coma and sweeping tail seen in most comets, Atlas displayed an irregular, asymmetric envelope of gas and dust. The coma spread unevenly, with denser regions offset from the nucleus and a diffuse, almost lopsided glow. The tail, usually a comet's most dramatic feature, was notably subdued, sometimes little more than a faint streamer, barely distinguishable from the background solar haze. Stacked images from SOHO's C2 and C3 instruments, along with Stereo A's CCOR-1, consistently showed that the coma extended farther on one side, suggesting a directional release of material or perhaps even fragmentation. The nucleus itself remained unresolved, hidden within this haze, but the overall shape hinted at a physical process not dominated by steady, sun-driven sublimation. Instead, the structure suggested abrupt or uneven outgassing, possibly triggered by external factors. Some color stacks revealed localized brightness enhancements in the blue and orange bands, likely tied to molecular emissions from volatile jets. Yet, the expected dust tail, bright, straight, and aligned with the solar wind, never fully developed. Instead, the tail appeared weak, sometimes curving or breaking up, and at times seemed disconnected from the main coma. These anomalies narrowed the field of plausible explanations. The evidence pointed toward a nucleus responding to more than just sunlight, and a coma shaped by forces beyond the usual thermal drivers. The puzzle deepened. What could account for such an odd, asymmetric structure in the wake of a historic brightening event? Solar physicists and comet researchers now turn to the plasma environment to explain the extraordinary brightening of 3I Atlas. As the comet rounded perihelion, it wasn't just sunlight at work. The 10-day barrage of far-side coronal mass ejections had flooded the inner solar system with shocks, high-speed plasma, and intense bursts of extreme ultraviolet and X-ray radiation. Each CME carried its own wave of energetic particles, compressing and stirring the solar wind into a turbulent, high-pressure sea. When a comet like 3I Atlas passes through these conditions, the nucleus and coma are exposed to far more than thermal heating. Charged particles from CME shocks slam into the surface at thousands of kilometers per second, driving a process known as sputtering. This bombardment can rip molecules and dust grains free from the surface, even in regions where sunlight alone would not be enough to trigger outgassing. At the same time, the surge in extreme ultraviolet and X-rays boosts ionization rates inside the coma, breaking up molecules and creating a cascade of radicals, Cn, C2, OH, seen as strong emission lines in the stacked photometry. The sudden compression from a passing CME can also squeeze the coma, raising local plasma density and temperature. These conditions accelerate dust fragmentation, releasing fine particles that scatter more sunlight and spike the comet's apparent brightness. Unlike the smooth, predictable ramp of thermal sublimation, plasma-driven outbursts are abrupt, chaotic, and can drive brightness increases by factors of 10 or more in hours. The timing fits. The strongest CME arrivals modeled by Stereo A and SOHO overlapped with the steepest rise in Atlas's light curve. The odd, asymmetric coma and weak tail structure further support a scenario where external plasma forces, not just the sun's heat, dominated the comet's behavior. For comet scientists, these plasma interactions offer a powerful, testable explanation for the super brightening and set the stage for targeted observations as Atlas continues outbound. The next opportunity to track 3I/Atlas falls to the ESA JUICE spacecraft. On November 2nd and 3rd, JUICE's unique orbit around Jupiter offers a clear, unblinded view of the comet as it emerges from behind the Sun. The mission team has reserved a 48-hour observation window, redirecting science payloads and shifting deep space network time to capture images and spectra. This is no routine task. JUICE was never designed for rapid comet follow-up, and the last-minute pivot required coordination across multiple mission teams. The goal is to secure high-cadence imaging and, if possible, catch any lingering outbursts or new structural changes in the coma and tail. Ground-based telescopes will soon join the effort, but only after Atlas climbs far enough from the sun's glare. Mid-November marks the likely return of faint detections from large observatories, with amateur astronomers poised to contribute through long-exposure imaging and stacking routines. For most, this means waiting until the comet's elongation grows past 20 degrees and twilight fades. Stacking remains the critical tool. Individual frames will barely register the comet above background, but by aligning dozens or hundreds of images along the predicted track, observers can build up a signal and track subtle changes in brightness or morphology. Anyone with access to a moderate-sized telescope and a sensitive camera can participate. The key is patience and careful planning. Check updated ephemerides, use precise tracking, and expect to spend hours collecting data for a single composite image. As the sun's active regions rotate toward Earth, these coordinated observations become essential, not just for understanding Atlas, but for monitoring the evolving space weather environment in near real time. Grid control rooms across North America and Europe are on alert as solar forecasters track the rotation of several massive active regions onto the Earth-facing side of the sun. The next 2 to 7 days are critical. These regions, responsible for the recent barrage of far-side coronal mass ejections, are now poised to send any new eruptions directly toward our planet. Magnetometer readings already show a persistent G1 geomagnetic storm, with intervals nudging into G2 territory as a high-speed solar wind stream sweeps past Earth. Operators at Hydro-Quebec and PJM have run through their load-shedding protocols, recalling the cascading blackouts triggered by the Halloween storms of 2003. Back then, a series of X-class flares and rapid-fire coronal mass ejections unleashed geomagnetic storms that knocked out satellites, disrupted high-frequency radio, and caused transformer damage across the grid. Today's conditions share more than a passing resemblance. The sun's magnetic complexity is at its highest in years, and the solar wind carries both speed and density spikes. Real-time alerts flow from NOAA's Space Weather Prediction Center to power companies, airlines, and satellite operators. Engineers monitor transformer temperatures and ground currents, ready to isolate vulnerable circuits if geomagnetic indices spike. Satellite controllers, especially for low Earth orbit constellations, watch for sudden increases in atmospheric drag that could throw off orbital calculations or even force emergency maneuvers. Amid all this, the aurora forecast lights up for mid-latitudes, just as it did in 2003. For most, it's a spectacle. For those responsible for keeping the lights on and the data flowing, it's a time for vigilance. The next major solar eruption could arrive with little warning, and the margin for error is slim. The operational focus remains clear: safeguard critical infrastructure, maintain communication, and keep a close eye on the sun's every move. Yet, NASA/JPL Ephemeris updates show no deviation from its outbound hyperbolic path. Stacked spaceborne imagery and ground-based confirmations verify the anomaly, while morphology remains unusual: a diffuse asymmetric coma and weak tail, unlike typical solar system comets. The leading hypothesis links this outburst to intense solar wind and CME-driven effects, but the exact mechanisms remain under investigation. As Earth now faces a 2 to 7 day window for active solar regions to rotate into view, operational agencies are on alert for possible G-scale geomagnetic storms, echoing conditions seen during the 2003 Halloween events. The full story of 3I/Atlas is still being written, but the evidence underscores one reality: our solar system is dynamic, and vigilance remains essential.